the final exam will be just on this third part. It's not cumulative. And there's no homework, no office task this week because we just had the exam. We'll assign the next homework on Monday and on 11/8. But just note, this is due off cycle on Friday. And that's because I'm traveling the week after, the week of 11/15. So, and this is all on the core syllabus, but I'm traveling, so we have only two problems. So that's a shorter homework. We'll discuss and make sure you have all the resources you need to have it. So the next week we'll have homework 5. We'll talk more about that next week as well. But basically homework 5, and then you have the Thanksgiving break, and then you'll have one more homework due for the finals. Okay, so 2 more homeworks remaining. The fifth one will be probably one of the shorter homeworks. It only has 2 problems. Each problem obviously has some parts, but it won't be too bad. And we'll try to make sure you have all the help you need. Okay. So, and just want to kind of, before we go into the details of what we want to discuss today, I think it's a good time to kind of reflect on what we have been discussing in part 1 and part 2, just so that you kind of refresh your memory of where we started. So in the part 1 of the course, we focus on sometimes this heat and heat conduction and species diffusion, right? And here, basically recall that we started with 1D study problems. We discussed gas phase diffusion, binary gas phase diffusion, liquid phase diffusion, so on. Then we went to approximately 1D study, still just focusing on the species diffusion or conduction. Sometimes we added a reaction. Then we went to 1D unsteady. This was the similarity transform and so on. And then we went to like 2D study or 1D study with reaction, which was the topic of finite Fourier transform, regular perturbation analysis, etc. Okay. So basically the first part of the course was really about, there are 3 parts of transfer processes, heat, mass, and fluid mechanics. So we focused more on the heat conduction and species diffusion. So that was the emphasis on part 1 of the course. And what you really learned was, how do you set up a problem when there is no convection, it's purely diffusive, and then how do we slowly build it up in the system. In the second part of the class, we focused on fluid mechanics, and the topics we focused on starting with hydrostatics. So you learned buoyancy force, so on. So hydrostatics. Then we had nearly unidirectional flow, which were either within a channel or something rotating, like a sphere rotating or a cylinder rotating, unidirectional flows. Then we started complicating things and adding new ideas which were nearly unidirectional flow, or just sort of simplicity, I'll call it lubrication approximation. And then finally we had the creeping flows, which could be 2D as well, right? So we again clearly, very similar ideas. You slowly add all these details, approximately 1D study, 1D unsteady. Here we had unidirectional, near unidirectional, and then finally 2-dimensional, which are creeping flows. In this part, basically the idea was, all of them we ignored inertia, no inertia. So this was the bulk of the last part. We focused on no inertia. And then finally, the last part we discussed was the potential flow, where we discussed there was only inertia. We didn't have any viscous stresses, so no tau. Okay, so the viscosity was 0. It was mostly driven by inertia. So that was kind of the broad structure. So now basically the basis is that we understand diffusion and conduction. We understand fluid mechanics until the point either the viscous dominates or the inertia dominates, right? And when I always start this class, I give some examples. In this year, we discussed examples like, we will discuss how the COVID-19 spread, how it has, these viral droplets coming out through aerosols and traveling. But remember, it's both it's a both mass and fluid mechanics problem. There is a mass transport of these viral droplets. And then there is a fluid mechanics which is happening in the background of these in the air. So it's a combined process, right? So it's a combined process. Similarly, if you look at some of the electrochemical applications, there is a combined transport of ions, while there is also flow of fluid mechanics. So again, it's a combined transport process. Similarly, also for something like a carbon sequestration, using these waves, which we are seeing, this is dissolved carbon dioxide seeping through water, creating these instabilities. And I think I showed this video early on in the class as well, where you can model it. And these are again coupled heat and coupled mass transfer and fluid mechanics equation. So that is something we have not done till now. Okay, so the part 3 will have basically this emphasis. Part 3 will have emphasis in these forms. So briefly, first a few lectures, which will be basically we'll finish the point where we will have both heat and mass transfer. So that's basically the boundary layer flows. So boundary layer flows. This is finishing the fluid mechanics part. And this is chapter 9. Okay. So chapter 9 will discuss what are boundary layer flows, and we'll start that today. Then we'll start to go towards these combined topics: heat and mass transfer with flow in confined flow. So this confined flow is like a channel. So confined flow in a channel. And why is that interesting? Because a confined flow, you can imagine, you can make it a 1D kind of problem. You have seen that now when you start to have one dimension dominating. That's chapter 10 in the book. Then we'll have heat and mass transfer in unconfined flow, that is around the object. So that is going over a sphere, chapter 11. Okay. And then finally, we'll have the final part being electrolyte transport, which is chapter 15. We'll skip over a couple of chapters that or I think 3 chapters, which focus more on turbulent flows and multi-component diffusion. That is something we'll not discuss, but you are welcome to look them in the book, or remember that when you're in your research, if there's something that comes out related to that, the book does have multi-component diffusion and turbulent flows, but we will not do that in this course. And so this is the kind of way we'll do. So we'll combine the analysis. So in the chapter, basically chapter 9 is finishing fluid mechanics. Then chapter 10 and 11 is combining what we learned with conduction diffusion with the fluid with the flow part. And then finally, electrolyte transport is now, we'll add a charged species. So remember that all diffusion we have learned till now is for a neutral species. Now we'll add a charged species. So we'll change the governing equations. So at the end, I just want to show you a multi-physics simulation where you now add more kinds of physics in it. So you can imagine you may be working with very complicated materials. They may not just directly use Navier-Stokes equation. They may have some other kind of physics that may come in. So we'll just end the last 3 lectures with kind of, just learning how do you approach a problem which is transport phenomena driven, but has more physics involved. Okay. So that is kind of the idea. Any questions on the plan, homeworks, anything for part 3 before we jump into the details of new chapter? All good. All right. So let's begin and let's discuss where we left off the class. So basically, inviscid flows is what we discussed last time. So you remember that in inviscid flows, we had done this in class. And you did this also in your homework problem, that we had flow over an object. We solved del square phi is equal to 0, right? And then we also had, or you can solve del square psi equal to 0 or E square psi is equal to 0, depending on the geometry, right? And then with that, we'll also combine this with pressure plus pressure by rho V square by 2 plus GH is equal to constant. So this is what we already did in the class, and you also did in your homework to find the velocities, and then you using this, the first equations, and then you use Bernoulli's equation to find pressure. So we could calculate VR, V theta, P, and then finally to calculate the force, we did this, and then we got minus N minus P and ds, and then that came out to be 0. right? So this was basically the D'Alembert's paradox. So remember that this is something you also showed in your homework. So this is where we were in the course. We said, well, you could essentially doesn't make sense that the force is zero, but we could solve the problem. So now I want to kind of build off of this, and so I think we briefly mentioned in the class is that this happens because one thing that I'm currently missing very crucially is that I'm not able to enforce a no slip boundary condition, right? Or a zero shear stress boundary condition, because because I've reduced the order of the equation, it is a second order equation in potential phi or velocity, then I'll only have two conditions, one at the surface and one at far away. I will not be able to impose a normal condition and a parallel velocity condition. And so this basically happens because there is lack of no slip. So in reality, if you want to think about this problem, basically what is happening is if just the same problem that we are solving, right? This problem we are solving, if there is no slip. So what's going on? Let's say there is no slip. So then there is the velocity is small, somewhere near the surface. Velocity is small here. Velocity is small in this region. Again, we'll define what the small is because of no slip. Right, and outside here, del square phi is equal to 0. Right? Isn't this kind of what we are saying is that there's this inner region. Let's share this with some other color. There's some sort of an inner region here. Inner region. And then there's an outer region. Okay? There's an inner region and there's an outer region. And that we are solving sort of an outer problem because we are not imposing this inner region. We are not being able to impose this no slip condition. And that's basically the whole issue is that in the outer region, basically outside, inertia dominates everything. So we can really assume that tau is 0. Right? But inside the inner region, viscous stresses and inertia are balanced. Okay? Are balanced. Okay? And this region is called the boundary layer. This inner region is called the boundary layer region, where the velocity, where the viscous stresses and inertia boundary layer region. Does the physically make sense that I have now, and sometimes students kind of like think about this, and this is the way usually I also think about it, that there are two regions, but in reality there are not two regions, right? This is a fictitious sort of concept that we are creating in our mind just to understand this problem better. That there's an outer region where this potential flow is valid, and then there's an inner region and we'll derive some other equations are valid. In reality, in both regions, Navier-Stokes equation is valid, but we can't solve the Navier-Stokes equation. So we're trying to create this sort of distinction in our mind, which is trying to kind of answer this question. So, okay, so does it make sense? This boundary definition, there is no exact definition. It's not like, oh, this is the boundary layer thickness. We will always estimate a scale of that value. We'll never have a region because that depends on our definition. In reality, this distinction is basically an artificial distinction created so that we can understand the problem and separate it into different parts. And then you can solve it. And this is extremely important. This whole boundary concept is like one of the most important concept in, reducing drag in systems and so on. So we'll discuss that in a lot of detail. But does this make sense physically? What's going on here? Any confusion here? Anything that's confusing, not clear? All good? Okay. So let's keep going further. So the next idea that we will basically discuss is how to think about this system in terms of geometry. So let's imagine that I'm sitting here EY and EX, that I'm moving my X direction is parallel to the surface, or like it's moving. It's not a constant EY, EX. I'm just saying EX is the longer surface, EY is perpendicular to the surface. So essentially, and I'll sketch this just for clarity. EY and EX, Y and X, and so you're going like this. In this region where the velocity is sort of developing from 0 to some scale of u, this is called the boundary layer thickness and boundary layer thickness. Okay. So you might wonder, well, how do I define this line? How can I just say this line? So people call it with different values. Some will say 99% velocity, 99% of u, 95% of u, where u being the velocity outside, the final velocity outside. People define it with all sorts of definition. Not important. So that's just like a matter of detail and being pointed to be consistent. In terms of an idea, it's basically the scale close to you. Okay, that for you could be 60%, could be 90%. That's up to you. It's not a definition, and we will not, for the purpose of this course, we will not try to worry too much about its exact definition. Okay, there are special topics in fluid mechanics where you can go into the details, but for this purpose, we will not talk about that. Okay. Yes. Delta, yes, delta. So I'll denote with this delta of x. Okay. Delta of x. Okay. Any questions here? Anything that's confusing? The question for all of you. Okay, sure, I have these two regions and I can solve them. Let's say hypothetically, I can solve them. But there's still a problem. I still need to find the solution which is valid everywhere. So how do you think I can connect them? Any thoughts like this physically? You can think about something or an idea. How do you think you can physically connect
superposition between the boundary condition at the boundary layer where and about?
So really very like, so almost the same idea. So exactly right is that we want to kind of connect. There is a boundary that we have created. So you have to think about a boundary condition, right? And this is a very common kind of misconception sometimes students have, is that there is only one boundary condition or something. The basic idea simply is that if I'm in the outer region, so let's imagine that this is my object, okay? The boundary layer is just here and air is happening here. Let's say you're sitting on the projector and then looking at this surface. Would you notice the boundary if it's just this thin? No, you just think it's the surface, right? And now, let's say the hand is here and the boundary layer thickness is here. If I'm sitting at the scale here, and I'm now like also a tiny person who's sitting here, trying to look at this hand, that would appear like a infinity solution. Okay, so that is the way to think about it. When I'm at this scale, for me, everything beyond that looks like infinity. But when I'm sitting at the projector and looking at the surface, this is like, I don't see the boundary. So the important point is that the outer solution. So the basic idea is this, that the surface boundary condition, how to connect the two regions. So the idea is surface boundary condition of the outer solution becomes the far field condition of the far field or far away. Far field, let's just call it far field condition of the inner solution or the inner region. Okay. So this is very important. This is one of the most important concepts about this idea, is that there is a surface, the potential flow is not a useless result. Okay, it is very important. It gets the boundary condition wrong. So we'll use that result to inform what would be my boundary condition for the inner solution. So you got out a slip velocity. So if you remember from a cylinder calculation, there was a slip velocity, there was some tangential velocity. That's not a useless number. That does kind of tell you what the far field condition should look like in the inner solution. Okay? So that is precisely important. In the inner solution, I know no slip, right? I can't see if you're sitting here, you won't be able to calculate until the projector, right? But from the projector, you can't calculate the surface. So to connect the two is the idea. So the far field, the surface boundary condition of the outer solution becomes the far field condition of the inner solution. That's the idea. It's very sort of this idea is very crucial because then this allows us to connect a very thin region to a very kind of like a large region. And we'll talk about some of the scales later on in the lecture. Okay. Any questions on this idea? Isn't that confusing? All right. Okay. So let's keep going further. So the goal is basically, that's a goal. So solve outer problem, solve outer solution. Okay. And then solve inner solution. And then connect the two. Okay. And then connect the two. And then connect. All right. So for now, for this purpose, maybe let me sketch it clearly here, then we can go further. So the problem we are thinking of is in this X and Y for visualizing this, think of this X and Y as something parallel to the surface and perpendicular to the surface, X and Y. Okay. And that there is some sort of velocity U coming in here. Okay. So if you are finding it difficult to just remember that I'm going like this on the surface. Okay. And the perpendicular is also sort of on a cylinder. I'm going like X and Y are rotating on the cylinder. And this is just to simplify the calculations a little bit. So this is perpendicular to surface. And this is parallel to surface. Okay. And then this length scale in X is about L. And this is about delta of X. Okay. Delta of X. This is what we want to solve. This is the problem we want to solve, where U is the velocity in the outer region. Outer region. Okay. So, and we'll discuss what this U means and so on. We'll talk about this. All right. So to solve in the outer solution, we know. So let's say outer solution now. So now imagine, just forget about the cylinder for a while. Just think that we have zoomed in and created this sort of a flat kind of geometry. Just to show you how the process works. All right. So in the outer solution, we get del square phi is equal to 0. That's the governing equation. We know this. P by rho plus GH plus V square by 2 is equal to constant. Right. And then let's take a quick question here. I believe that should be here to sort of motivate this question. So we are trying to solve this problem. Okay. How will you solve in the outer problem? The velocity. So let me just go back here. So I'm in the outer solution. So I'm here. Okay. So I'm essentially somewhere here. Okay. Essentially like this. And then what is how you think we would do how will I set the boundary condition? Okay. How will I obtain the velocity Vx at y equal to 0? All right, maybe another 5-10 seconds if anybody else wants to get their answers in. All right, I'll close it now. All right, so I think 3/4 of you think it's potential flow, and a quarter of you have the answer is no slip. So there are two confusions here that students get. Okay, so some students think, well, it's potential flow, so we should not have no slip because it's an outer solution to potential flow, which is majority of you. Then some of you, some others who probably chose no slips thought, well, y equal to 0 is the surface. So how can I have a potential flow there? So I need a no slip. And that's the confusion I want to address at this point is that, so you cannot apply no slip. It has to be found by potential flow. But that does not mean that y equal to 0 does not exist in my outer solution, which sounds confusing. So again, think you are at the projector and you are looking at this surface here. Does it matter to you whether you're solving at my hand or at the surface? No, it's still y equal to 0 for you. So y equal to 0 exists on both the potential flow and the inner problem, but the meaning of y equal to 0 is different. When you are at the outer solution, y equal to 0 represents something that's near the surface. And let's say if you are, let's say, 100 times the size of this, let's say, this surface, you're 100 times away. For you, 0 means, let's say, 10 about the length of this is still the same because you're 100 times far away. So 99 times you have gotten closer to the surface. That's really the surface for you. But when you're in the inner region, it is the true surface which is y equal to 0, right? So go ahead.
So what we're calling the zero outside is delta of the.
Close, yes, it's not exactly that. So close. So Tim is asking a very good question. Is it delta? Like, how do I think of the y equal to 0? Is it real delta? Rather, the way to think about this is this. Think of it like this. If my Vx is a function of x and y in the inner, this infinity is equal to Vx of outer of x comma 0. Does this make sense mathematically? Okay, go ahead.
So are we solving with discipline on the outer and it's not in discipline on the inner because it's most anything in this book?
Correct, absolutely. So basically we'll discuss how to solve the inner. We haven't discussed the inner. So outer is potential flow, but what I'm saying is that, so this is very important. So what Tim was asking was, well, aren't we kind of saying that far away, delta is my kind of the region that I'm solving for? Yes and no. The point is that boundary layer does not exist for the inner and outer solution. Again, that's a concept in our mind. Outer solution thinks there is some slip. Inner solution thinks there is no slip. And the slip of which is the slip velocity from the outer solution, which is the right hand side of this expression, this part here, is sort of the slip, right? And that becomes a far field condition from the inner. It's infinity. If you don't say delta, what I was trying to get at is because delta is again something that we create. And what Tim is asking is actually the famous solution called von Karman solution, which actually kind of proposes that idea that we force it to be a delta. That is something you will do in your homework. Okay? But in reality, this is more exact. It is saying that the inner solution, far field of that, is the outer solution surface solution. Okay? So we'll do the delta analysis in your homework, but I just want to clarify it doesn't have to be that. Okay, that's an approximation. That's not a this is a more exact result in terms of like purely mathematical. Okay. Any other questions here? Yes, please.
So, at what kind of length goes?
Great question. So that actually depends on the Reynolds number. So we'll discuss that in a bit. That the delta is actually it depends on the Reynolds number. So your Reynolds number have to be large, and by large I mean something on the order of 10,000s to millions. Okay? So we'll discuss that in a second. Okay. Good question. Any other questions? All right. Okay. So I hope this is clear. We know how to do the outer problem, and then we'll connect it to the inner problem. By then, so outer problem we know. So one thing I want to kind of say is if you ignore gravity for a second, ignore G for simplicity, and we can add it. It's not a problem. Then you will get P by rho plus V square by 2 is equal to constant, right? And outside do you agree if I say V is equal to U? Why do I not have a normal component? So V square is, remember V square is V parallel square, this is a U parallel square, this U perpendicular square, right? Why do I not have a U perpendicular? I should have it. Because your no penetration is still valid, right? So if you remember that if you do apply a boundary condition, you cannot have necessarily a perpendicular component in the outer solution. So that's why V is simply this. So we can say P by rho plus U square by 2 is equal to constant. And this is basically the parallel slip velocity. Right? From outer solution. From outer solution. And what you basically get, you can show is dP by dx. You differentiate with x. This becomes minus u du by rho u du by dx. Sorry, I'll just write it clearly, minus rho u du by dx. And in case this is not clear to you what u is, I just want to explain this. This is the solution of Vx at x comma 0 is equal to u of x from outer solution. Okay, so this is the value you calculate. The slip velocity you calculate. I'm just putting this into the Bernoulli's equation and calculating a relationship between the slip velocity and the pressure gradient. I will discuss why this is important. This is just something I want to get ahead and just show you this one. Okay. Any questions here? I want to go through this slowly because I realize this is one of the more involved topics here. So I want to make sure everybody is clear. All good. All right. So now let's go to the inner solution. So inner solution. So outer solution, basically solve the potential flow. You get out the slip velocity, put this in the Bernoulli's, and you get this as a result. Okay. Now let's go to the inner solution. So how do I do my inner solution? Any thoughts, ideas? Navier-Stokes, right? That equation is always valid. So Navier-Stokes is always valid. It's never not valid. So it's always valid here. So del V x by del x plus del V y by del y equal to 0. Then we get x momentum is rho Vx del Vx by del x plus Vy del Vx by del y equal to minus del P by del x plus mu del square Vx by del y square. And obviously we are doing a two-dimensional calculation. Del x square and then del y square. This is the full equation that we can solve in inner problem. Any questions for this setup in the inner solution? So what did we do in the outer solution? We said this right hand side is 0, right? This right hand side mu terms are the problem. In the outer solution, we said this cos thing doesn't matter because the Reynolds number is so large that we can just crop out the right term. Now we have reintroduced them in the inner solution because we said if you don't reintroduce them, then I can't do the no slip condition. So I have reintroduced them now. Now, what next? Should we just solve this now? Sorry. So good question. I'll just come back. Yes. So the question is the session is, can you just cancel the inertia? So we don't know, right? That's not necessarily we can just cancel it, but yeah, good. Yeah. All right.
the delta X on by the lubrication.
So great, excellent question. That was actually what the answer I was looking for is that now we are thinking of, we have to do an order of magnitude analysis, assuming that the boundary layer thickness is much smaller than the length scale to simplify these equations further. Right now, they're too complicated to solve. There is three variables, Vx, Vy, P, have each of them have dependent of X and Y. And then it will be very difficult to solve this equation clearly. And so basically the next step is to actually simplify these equations further. And those equations are called boundary layer equations, and that is what we'll basically derive after the break. The next step is order of magnitude analysis on this equation. Order of magnitude analysis. I just want to clarify one thing. So order of magnitude analysis, while assuming delta by L is much smaller than 1. And then I want to answer the question why these are not lubrication equations. Because remember that lubrication equations require Reynolds numbers times H by L to be smaller than 1. Right now, my Reynolds number can be very large. So even if my delta by L is much smaller than 1, it doesn't necessarily mean that my Reynolds number times delta by L is much, because Reynolds number is very large. So I'll explain and show you how these equations are different than the lubrication equations, and then in the next lecture we'll learn how to solve them. Okay. So that is what we'll come back to. So let's start at 12:46. So let's take a 5-minute break and then we'll resume and start to do order of magnitude analysis. Yes.
Can't you say that the Reynolds number is small in the boundary layer since the velocity is going forward?
So it's right, but you cannot say that. You can say that it's so what does happen is they are comparable. So they're not extreme. The other side means they are energy are dominant. So it's small, it is costly dominant. But what happens is we don't go from inertia dominant to costly dominant to you have to get a balance, which makes sense.
I guess I didn't know that since the velocity itself changes, it must have no viscosity, right?
Oh, so you're saying I redefine a Reynolds number in a way? That's possible.
Because it's like, is it velocity times rho times
Yeah.
something like mu,
Yeah,
right?
of course, so technically, let's put it this way. What we're saying is the Reynolds number is, okay, it's not this straight. So what we're saying is this is much bigger, much more power because it's much bigger, right?
Right.
What I'm saying is. You're essentially having another definition there, within the boundary there. Yes, because saying.
But it's very like, small.
Oh, yes.
Distance from.
Yeah.
Right, well, or if the velocity is very small, because as you get close.
Both of them are. So they're definitely thinking of the surface, you will have. So I would say what average is the boundary there.
I see, but and it's also high rental numbers, you get it, you're gonna, right, so these.
Right, so this is currently assuming that we have not reached the point where what is eddy formation. That was separated as so these are called laminar boundary layers.
Right.
But after that, I something we don't know. Your that's and then.
Well, I guess the question is, like, when we have, I guess we learned undergrad that at a certain, you go from laminar.
Right.
And like, is that a correlation only true for water? Or for liquids that behave very similar to water, or like?
Broad, basically, like what happens is like. So you can here like high school, right? So basically, what this feature we are talking about is Yeah, this will be
And things were all that time, you know, it's sort of.
All right, let's begin. So 5 minutes are up. Let's start to think about the order of magnitude analysis. So we want to derive boundary layer equations. Boundary layer equations by through the delta by L smaller than 1. So how should the Vx scale as? It should scale as U. So we'll first start with continuity. We'll start with continuity. Vx scale as U. How should I scale X or delta X as? Any thoughts?
L.
L, right? Good. L. Perfect. Then I should scale Vy as something we don't know yet. Is a question mark. Delta Y should be delta. Okay. So if I do this, if you apply the equations now, Vx by delta X is similar to Vy by delta Y. And then this will give you Vy is similar to U delta by. So I just want to show this is what you will get U delta by L. Any questions here? Hopefully this is clear. Is that the velocity y direction is very small, clearly compared to the x direction. Any questions here? All good? All right, let's keep going. Then we have x momentum. So let me just copy paste this equation. Copy paste this equation here. And let's go term by term. Okay. So how should I scale this? Rho U square by L. Does everybody agree with this? Vx scales as U, delta Vx, or Vx also scales as U, delta X as L, capital X, right? This is rho U square by L. Then I have rho Vy, U by delta. Does everybody see this term, second term here? All good? All right. Then we don't scale the pressure gradient like the lubrication problem. Remember, we didn't scale the pressure gradient, so we leave it like that. And then we have this one here. This is mu U by L square. And then this one is mu U by delta square. Okay. Oh, so think of it like this. We are not ignoring pressure. The basic idea behind pressure is generated by balance inertia or the resistance. So we are not trying to. So good question. So the question is, why do I get to ignore pressure in a way? So think about this, the whole idea is not to essentially in the far limit, in the outer solution, it is inertia dominating over the viscous part, right? And now we're trying to balance inertia and viscous inertia, right? So the pressure is sort of an additional contribution. It can go to zero, and you'll see actually a problem. In some cases, it can go to zero, but it's not a competition between the two stresses. So this, and I'll show that actually today itself, this actually depends on something that the outer solution does, but in a simple case, think of it like this is a competition between an inertial stress and a viscous stress. That's what we're trying to do. In lubrication, for instance, we could just ignore the inertia completely, right? And then we had one term left on the side, right hand side. So right now, we cannot just directly say that because we're trying to kind of balance this in the boundary there. Outside, we know the right hand side goes away, right? All right, so let's start to drop some terms off. So on the right hand side, does everybody agree? I can drop this term mu u by square, right? Because length is L is much greater than delta. So I mean this term with the larger denominator, so the whole number is small. So I can drop this off. How can I further simplify my left hand side? So I have a Vy and I have a delta. So remember we have that Vy by delta from the continuity equation, and I can call this as Vx by L is similar to Vy by delta, right? Or U by L is similar to Vy by delta, right? So this Vy by delta could become Vx by or U by L. Okay. So in a sense, this becomes rho U square by L. This becomes rho U square by L. And then this becomes here, the full thing becomes mu U by delta square. Okay. So we'll make the delta better, delta square. Can I drop any of the terms on the left hand side? The two terms, there are two initial terms, right? Can I drop any of them compared to each other? No, right? But we also don't need to carry the two because you remember that in order of magnitude analysis, we don't have to say, 1 plus 1, like, so we don't carry the number. So essentially, I hope you can see rho U square by L scale as minus del P by del X plus mu U by delta square. Okay. This is basically what we get out. Okay. Does this make sense? I hope this is clear for everyone. Yes, please.
You say again why you crossed out the new view of L.
Sure, yeah. So basically what I'm saying is that this portion here, remember that if I take the mu U by delta square out, this will become delta square by L square plus 1. So the delta by L is very small, so I can essentially cross this. Make sense? All right. So now, very important here is that note that in this at this scale, all three terms are in balance to each other. Okay. So all three terms are balancing each other. Remember in the case of lubrication, and that was the question asked, can I use lubrication? We could just drop the left hand side because we were trying to divide it and showing Reynolds number times mass, but we cannot do that anymore. So all three terms are balancing each other. So all three terms balance each other. So that means that del P by del X goes as rho U square by L, and mu U by delta square also goes as rho U square by L. Okay. Any questions at this point here?
We're just scanning when we carry them.
Yeah, you don't have to carry. This is just you don't need to carry around this. Definitely you can just write this. All right, so this is first point. And then let's do one thing further here, push this a little bit. So you can see delta by L, and I will let you do this yourself if you would like. You will find that you can write this if you do a little bit of rearrangement, you can write this as Reynolds number to the power of minus half, which is a beautiful result that comes out from the simple scaling analysis. Very, very instructive. So you can simply just take a second to, if you would like, to just like think, I've taken a delta square there, I rearranged, you will get out rho u L by mu is for a half, or Reynolds number to the power of minus one, where my Reynolds number is rho u L by mu. This is my choice to define it like this. You can say, oh, I don't agree with this Reynolds number definition. That is definitely a reasonable argument, but this is just a choice for now. Okay, just to say, I know the scale U, I know the length scale L. This is what I will define. What does this tell you? This tells you that if my Reynolds number is very, very large, delta will be that much smaller. And so the higher the Reynolds number, the more thinner this region would be, this boundary layer region would be. And we were just pushing it to extreme. When we said infinity, we assumed it to be zero. But in doing so, we forgot that we are missing out a boundary condition, right? And that's what causing the whole problem. So this is kind of trying to say there's a big difference between exactly zero thickness and just about approaching zero thickness. And that is because this thin region creates all the difference. Okay? And so it's very clear that this region is thin. And this is one of those times that think about it, that till now we were working so hard to find problems where there was a thin gap. Here there is no thin gap. There is only one length scale L. The other length scale comes out of the flow property. So there is no other geometric constraint. It's just automatically a thinness has been created because of a higher Reynolds number. Okay, it's very important. Yes.
Sorry, you just repeat why you do like, don't need as, is like, these are all three terms balance each other.
Right. Yeah. Yeah, so that's a good question. So what I'm trying to say is that, remember that if I was to ignore this left-hand side, right? Let's say if this was small compared to, let's say, the other two terms, then you would get a lubrication problem, right? And we are not going through this, but it's exactly the same thing, right? And del V by del x is equal to mu del square dx by del y square, right? And if I were to ignore this term, the mu by delta square, then I get back the inertia problem, which is the potential flow problem. So the whole point of this boundary layer is so that we can get a region where these two inertial stresses and viscous stresses are balancing. And pressure has to kind of balance the whole equation, and that's why that is being added. Okay. So the pressure part is a little fuzzy. I understand it doesn't sound as natural, but like you just like the way you kind of can reason out, and that is the way I have reasoned out. It is like okay, these things have to balance each other. But it doesn't have to be. W by X doesn't have to be. It can independently tuned. It can be zero, but it never overwhelm the equation. That's the point. It just either balance them or be completely negligible, which is what we will discuss later. So that is the idea, that if I kind of either just go this limit, then I'm going to lubrication. If I'm going this limit, then I'm going to the potential flow. I'm somewhere in the middle right now. And that's the boundary flow. Okay. Any other questions? This is a very important concept, so I want to spend time on this. All right, so now next step is I would like all of you to write down the y momentum equation and do an order of magnitude balance. It's 12:58. I'll give 5 minutes. Take your time, balance it out. And what I would like you to write down is the scale similar to this. Write down the scale of del P by del Y, what the scale comes out to be, and also what do you get out for delta. Okay. So what do you get anything else for delta? So y momentum. Let's do the order of magnitude analysis. So it's rho. I'll just write down the equation just to be sure, and then you can all do the order of magnitude analysis. All right. Okay. So please do this. I'll give plenty of time to kind of do this. And you can please people to talk to each other. All right, maybe one more minute. Please people to talk to each other. If you have make progress or compare your answers. Please do feel free to do that. All right, so maybe we can start to discuss. Hopefully, many of you made progress and kind of saw how these different terms work out. So I have written here it's Vx Vy by L, rho Vy square by delta, and then we got Ly, mu Vy by L square, mu Vy by delta square. So hopefully this is not confusing. Any confusions in the scaling these numbers? So V del U over del X is V over delta, del U Vy is Vy by delta, and because there is another Vy, there is Vy square, Vy over L square, and Vy over delta square. So we can cancel this term out here. Because again, same idea, length is much bigger than delta, so we can cancel this out. Now at this point, there are two approaches to this, and you can choose either or. So simply you can see that this is Vx by L from continuity is same as Vy by delta, right? So the right hand side, so the left hand side really becomes here rho Vy square by delta, and this is minus del P by del Y. And then this is plus mu Vy by delta square. So again, we are saying three terms are comparable. We'll say del P by del Y is mu Vy square by delta, and and we'll say, sorry, my mistake, rho V square by delta, rho V square by delta, and then we'll say, so comparing these two, and I'll compare these two, that rho del mu Vy by delta square is rho Vy squared by delta. So this gives us the direct comparison of del P by del Y, and if you rearrange this, actually in terms of U and L, which is what we would want, then first this delta gets cancelled. One Vy just gets cancelled, so I get mu by delta is similar to rho Vy, which is equal to rho U delta by L. Okay, so I have just basically shown you how we can get to this point. And then from here again, you will get delta is 1 by rho U L by mu. The power of delta by L is equal to this. Okay, so you will get the same approximation out for from this result. Okay, so you can verify this. Don't worry if you kind of don't see the full, but it's not that difficult. All you need to do is make sure at the end you substitute V bias, you do delta by N, right? Because you know U, you don't know Vy, right? We know U, so that's why at the end you always want to express in terms of capital U and L, and you get this out. Okay? So that is my boundary scaling analysis, and both x momentum and y momentum is the same, which is what it should be. If I get a different scale, then obviously I'm doing something wrong, right? This means that delta does scale like Reynolds number to the minus half. But there is one other interesting feature that comes out of this. And what do you think is that? Do you think there is something else we can try to conclude? Similar, think about your lubrication idea, similar idea here. Is that we want to think about the pressure dependence as well, right? So we had taken a ratio of del P by del Y and del P by del X earlier. Same thing we'll do here. So let's take a ratio of del P by del Y and del P by del X. So that was rho Vy square by delta by rho U square by L. Okay, this becomes Vy square by U square into L by delta. And this becomes delta by L square into L by delta, or it becomes delta by L, which is much, much smaller than 1. Okay. Oh, sorry. The screens are not aligned, so just give me 1 second. Okay. So yeah. So rho Vy square by delta, rho U square by L, Vy square by U square, and L by delta. This is delta by L whole square. So you get smaller. So what does this mean? That on top of everything we were doing, pressure does not depend on Y. So this implies that pressure is mostly dependent on X. Pressure is only a function of X. We have not established anything else. We do have Vx and Vy with both X and Y, much like lubrication, but pressure is only a function of X, also similar to lubrication. Okay. So what does this mean? If pressure is only a function of X, how does it help me? Any thoughts? Any kind of? Great. So yeah, so I think we are going in the right direction. So let's try to, great idea. So let's try to just basically go further now. Is write the equations. Okay. So our governing equations now. Governing equations now are rho Vx del Vx by del X plus Vy del Vx by del Y is equal to minus dP by dx plus mu del square Vx by del Y square. Okay, so I've dropped the second term. Remember, there is only one term I could drop. Okay, there was only one term I could drop. I have to keep all of these other equations here. But on top of everything, I could say that pressure is only a function of X. That is one approximation I could make here. And we also have the continuity equation. So what Tim was saying, that we can kind of now go about this idea of using continuity and this together to solve it. Okay? That's precisely correct. But I want to push this further. Because remember, this is just the boundary layer equations. And when I'm saying pressure is function of X, again, don't forget this, here we have the camera. Now here, if my pressure is only a function of x, does that mean it will change in this direction? No, right? So, and what we within the boundary layer, what do I expect it to be when once it kind of goes a bit further away? It should match the outer solution, right? And remember, from our outer solution, we had written dp by dx is minus rho u du by dx, right? Why am I able to write this, match these pressures? Because they don't depend on y. So whatever my x gradient outside is has to be the same gradient inside, because they have to match it in the y direction, but there is no dependence in y. So that means that I can directly put that there. So if you put it there, essentially what you get is the celebrated equations. These are basically, if you put this, you'll get del p, del v x by del x, this del v y by del y equal to 0. And this basically is rho u du by dx from outer solution. Outer solution, then here we'll get vx del vx by del x plus vy del vx by del y. I'm taking a step further, u du by dx plus nu, which was the kinematic viscosity. These are our boundary layer equations. So these are boundary layer equations for flow, and they have extremely important for fluid mechanics and for general engineering around on drag calculations. Okay. So what have we done? We first did the order of magnitude analysis and said P is only a function of x, but because of matching, we basically went and did the we got the rho u by dux. So this is a slip velocity. This is essentially the slip velocity entering here. Okay, and this, by the way, is mu by rho. So what this mu is mu by rho. Remember that it was something we discussed long back as the units of meter square by second. This is how we get it. Does it make sense? Any questions here? U du by dx. So u du by dx. This is u du by dx from slip velocity. Everything is on from the outer solution. All right. Now, so the question was, is this lubrication? So in lubrication, you would not have u du by dx. You would just leave it at minus dp by dx and plus mu that's equal to y square. The left hand side would not be there, right? So from that perspective, let's take a quick question from the polls. Is unlike the lubrication approximation, what is true for boundary layer equations? And let's just discuss that. All right, so maybe another 15 seconds or so, just so that you can get your answers in. All right, so let's stop it here. Hopefully, all of you, yes, so it is all of the above, right? So that was the idea, is you have to think about like all these different effects that are not present, and so all of them are correct. So all of you who are even selected other options are right in that way. But these are all the complications that you get in the system, because remember we utilize the thinness of due to high Reynolds number to get the delta. These equations are non-linear. That is very important. Remember that we are not no longer ignoring this Vx times Vx comes now. So they are non-linear. So they are not as straightforward to solve like lubrication. And then very importantly, normal component of the velocity affects flow. This is something that is very unique. See that the Vy is still in the Vx equation. Vy still is a Vx equation, and that actually ends up becoming quite important, and as we'll see later down, okay? So this is essentially what we will solve in the next lecture, but I want to end with something very interesting and something I find very fascinating about this is that the next thing is basically we'll solve boundary layer equations. So I'll call them BL equations, boundary layer equations over a flat plate. Over a flat plate, okay? And this solution is known as the Blasius solution. Blasius solution. This is what we'll discuss next time and how to solve the equations we saw. And this was a very, very critical result because it could for the first time, explain how to get drag in higher Reynolds number flows. Before that, theoretical fluid mechanics was not considered to be very credible because it wouldn't get the drag even with the calculations. So this is a very important result. But there is a very nice article. If you have time, I invite you to kind of read this. It's about Blasius's life and how, just like you all, Blasius was a PhD student. He was the first PhD student of Prandtl. And he actually felt like he was not very intelligent and couldn't really do much, and hadn't really realized what his results would mean, even a century later. Okay, so to me this was like, I mean, you can read the whole article. A lot of self-doubt, which you all obviously have, but understanding that is how science works. You feel like it's not maybe important what you're doing, or it's not as you may not have those abilities, you might think that way, but that's also how Blasius thought about himself. So a very nice article if you want to read. It's in the Experiments in Fluids, and I actually read it myself when I was preparing for the course. It's a very fascinating read, so I invite you to check that out. Okay, so with that, let's end the class here, and then we will continue on Monday and discuss how Blasius solved this problem.